We'll start in a minute. All right, it's 1:10. So exam 2 review. Let's talk about what's going to be on there. This is just posted on the exam 2 information page that she has up. The sections are essentially 7.4 through 7.9 to as far as content, that's partial derivatives. So everyone's aware of what we're responsible for. And we have extrema of two variables, meaning finding the partial derivatives, setting equal to 0, finding the points, and then the value, or then classifying based on calculating d equal to fxx times fyy minus fxy squared. We have Lagrange. Usually on an exam, you will be told to use Lagrange if they want you to use Lagrange, like it would just be like randomly, here's one you should know to use Lagrange on. We have double integrals. Okay, all right. Good to know. So the thing is, when we do so extreme of three variables, that's probably going to be a Lagrange situation. But so typically, like if you wanted to maximize a function of three variables, often that's still a situation where it really ends up becoming like a function of two variables because you've got some sort of constraint where it allows you to solve for the third variable in terms of the other two. So usually we don't, I mean, it's not something we typically encounter, or if it is, we do use Lagrange for it. But like, and if you have an example, I can certainly like talk about that, but usually we can kind of do either way. And then there's applications of double integrals, which mostly I think of as like the average value stuff. And then finally, we have the things in sections 10.1 and 10.2, which are sequences and series. And for the most part, I think for series, we just have, specifically for the series, we have the nth term test, which shows things diverge, or we don't know, and we have geometric. So far, I think those are really the only two series, other than just like saying like, you could be giving a finite series and ask what do these terms add up to. So there's certainly things we can do with finite series, but as far as infinite series, I think those are the only two things we've really talked about so far. Unless you talked about more stuff in class today, which I imagine you might have, but I don't actually. Sorry about maybe. Okay. You talk about like the comparison test, maybe?
Ratio test?
Okay, yeah. So yes, it sounds like today you talked about things which I plan on talking about on Wednesday after you have your exam, so that we can see. So let's do some examples of each of these things, and then if you have questions or the things that we want to see or have like a three variable problem, I'm happy to do those. Just chime in.
Are you gonna put out a
Yes. The plan was to write it over the weekend. You know how the weekend goes sometimes. But yes, I currently am partway through writing one. The intent is to have it written today. I will have it written today, and then I'll put solutions tomorrow. Sometimes the weekend gets away from me. So, exam to review. I'm going to start off with a partial derivative problem. So let's say we're given the following. So we're given f of x comma y is equal to y e to the x squared plus x divided by y. And we're asked to find the following. Part A, we're asked to find del squared f del x squared. In part B, we're asked to find fxy. So to find either of these, we first have to find the first partial derivative of x. So I would probably, even though the problem was written like this, I would rewrite it as fxx just because I find my notation more convenient. So let's see here. My fx, if I look at this here, I've got y e to the x squared, so the y is going to hang out. And the derivative of e to the x squared is going to be e to the x squared times the derivative of x squared, which is 2x. Here, I might think of this as x times y to the negative first. So when I differentiate the x times y to the negative first with respect to x, I just get 1 times y to the negative first. That's not too bad. And then my fxx is going to be a little bit gross. I'm going to have to use the product rule right here. So this y times e to the x squared times 2x, the y is a constant that's going to hang out. But then for the e to the x squared times 2x, we have to use the product. So the derivative of e to the x squared is going to be e to the x squared times 2x, and then we have to multiply by the other 2x. And then flipping it, we have to leave the e to the x squared alone, and the multiply by the derivative of 2x, which is just 2. And not that you need to write these things, but I'm kind of thinking of this as like u, and this is u prime, that's v, and then that's my u, that's my v. Just kind of show that I really do have the pieces of the product that I need. And then plus nothing, because the derivative of y to the negative first with respect to x is going to be 0. So I don't need anything else. So that's my final answer for the first part, is y times all that. And yeah, we could make it look nicer if we needed to, but we don't really need to. And then for fxy, we've already done the first step. We already know that fx is equal to that right there. Y times all this stuff plus y to the negative first. And then the derivative of that with respect to y is actually pretty great. Y times all this x stuff, the derivative is going to be just 1 times e to the x squared times 2x. And the derivative of y to the negative first is going to be negative y to the negative second. And that's kind of all there is to that. So just the general reminder that when you're differentiating, when you're doing partial derivatives, whatever you're differentiating with respect to, we're treating every other variable that might be there as a constant for that particular part of the process. Okay, let's look at some problems where we have to find and classify some relative extrema. So we're given f of x comma y equal to 1 minus x squared plus x squared y plus y squared plus 1/3 y cubed. And we're going to find and classify all the extrema, all the relative extrema for a local extreme. So first things first, we're going to take the partial with respect to x and with respect to y, and set them both equal to 0. So also I'll point out, right, this is definitely, we could not do, if the question says you have to classify the extrema, that almost always means you need to do it this way and not use Lagrange. Also, this wouldn't be a Lagrange problem because there isn't a constraint. So you got to have a constraint to be able to do Lagrange. So here we're just taking the partials. So my partial with respect to x is going to be negative 2x plus 2x times y. I'm going to set that equal to 0. My partial with respect to y is going to be a little more complicated. It's going to be x squared plus 2y plus 1/3 times 3y squared is going to be just y squared. That equals 0. It's almost always the better bet to try to deal with the one that looks simpler. To me, that looks like the first one. I can factor out a 2x. If I factor out a 2x from this one, I get 2x times negative 1 plus y equal to 0, which leads me to two possible solutions. Either x equals 0 or y equals positive 1. And I should stress every time, when you get two different solutions from the same equation, that point 0, 1 is not a critical point. We're not saying x is 0 and y equals 1. Because if x is 0 and y equals 1, yeah, this would be 0, and this would not be. If x was 0 and y was 1, you'd get 0 plus 2 plus 1, which is 3. So if x equals 0, then we take this equation and we take two different paths. Here's the path where x equals 0. We plug in x equals 0, we get 0 plus 2y plus y squared equal to 0. And then we solve for y. We factor out a y, left with y times 2 plus y equal to 0. So we either get y equal to 0, y equal to -2. So we have two critical points just from x equal to 0. We have both 0, 0 and 0, -2. And then we do the same thing, but we plug in the other solution over here, which is y equal to 1. So plugging that in, we get x squared plus 2 plus 1 equal to 0. Oh, good. I was hoping this was going to happen. Sometimes when you plug in one of the other values, you get no solutions. So here we would get x squared plus 3 equals 0, or x squared equal to -3. And we're like, oh no, we're not going to get any real solutions here. So I don't anticipate that happening, but it could happen where one of those two critical values from one of your partial derivatives yields nothing in the other equation because it's just not a solution. So here we only have two critical points. We have the point 0, 0 and the point 0, -2. So now we have to find the capital D and plug each of those points into that to see if it's a max, a min, or a saddle, or potentially inconclusive, but hopefully on an exam it wouldn't be. So let's see here. We're going to find capital D. So I need my fxx, which is going to be, I'm just going to look at fx and take the partial with respect to x. I'm going to get -2 plus 2y. My fyy, I'm going to look at fy, take the derivative with respect to y and get a +2 plus 2y. And then finally, fxy is going to be the derivative of fx with respect to y, which should be 2x. I always like to do a double check and do the other one with respect to x. So if I take the derivative of this with respect to x, oh yeah, it's also going to be 2x. So I'm good. And then we're going to write out capital D. Capital D is fxx times fyy minus fxy quantity squared, which in this case ends up being -2 plus 2y times, oh, sorry, did I make a mistake here? No, I didn't. No. I thought I did. So it's a little strange to me to see that both fxx and fyy only have y's in them, but it's totally fine. It happens. Yeah, that's right. Yeah, I just feel, yeah. And then minus 2x quantity squared. And I would not simplify this. I don't think there's much to be gained, really nothing to be gained by multiplying this out and simplifying it. All I want to do is plug in each of my critical points and see what happens. So I'm going to plug in 0, 0, and get -2 plus 0 times 2 plus 0 minus 0 squared. That's going to be -4, which is negative. And when D is negative, we have a saddle. Saddle at 0, 0. And then we'll probably get something different at the other critical point. Let's plug it in. So the other critical point was 0, -2. So we're going to get now -2 plus 2 times -2 is -4. And then over here we have 2 plus 2 times -2 is still -4. Minus 0 squared. So here we're getting -6 times -2, which I don't really care that it's +12. I just care that it's positive, but it is 12, which is positive. And then since I was smart, I think, and didn't multiply it out beforehand, I can see that the thing that was either fxx or fyy, either one of those is going to be negative. fxx is -6, fyy is -2. So since fxx is negative, that means we're concave down. And really, I do like to think about it being concave down, which means we have a maximum at the point 0, -2. You don't have to write all that. Right? If you just write like fxx is negative, and then that goes straight to saying that you have a maximum, that's fine. But I definitely always think of it, oh yeah, I think my second derivative is negative, I'm concave down, I have a max. Or my second derivative is positive, I'm concave up, I have a min. but that's the thought process I would. Okay. Questions about that? Before we do a Lagrange one here. Okay. Yeah, we'll do that one. So let's say we have the following situation. Temperature at any point on surface given by x squared plus 2y squared plus 3z squared equal to 30 is given by the function capital T of xyz is equal to 2x minus y minus 3z equal, sorry, just that's it, period. Find the hottest and coldest points. Or in other words, find the maximum and minimum value of this function, subject to this constraint. We totally could do this the way we did the previous one, with some work. If we took our constraint, although it'd be kind of gross, and so I should say, when things start getting kind of arithmetically or algebraically not nice, that probably means you want to do a different thing. Like here, I could solve for z. It'd be gnarly. I'd have 3z squared equal to 30 minus x squared minus 2z squared, and then divide by 3 and then take the square root. So I could say that z equal to the square root of some gross stuff, plug that in here, then I'd have a function of two variables, which we could then maximize in the way we just did in the previous problem. And that would not be the right way to do this problem. It would be really, really terrible. So here, since we see a pretty obvious thing we want to maximize and a constraint, it seems like they're leading us down the direction of using Lagrange multipliers. So we're going to use Lagrange. Because I see thing I want to maximize and constraints. So rewriting them in sort of standard way, my little f of x, y, z is 2x minus y minus 3z, the thing we're trying to maximize. And my little g of x, y, z is x squared plus 2y squared plus 3z squared minus 30, because we like to bring everything to one side and we're finding the constraint. And it's equal to 0. So then we write our capital F of x, y, z lambda as little f, 2x minus y minus 3z minus lambda times little g, x squared plus 2y squared plus 3z squared minus 30. And then we take all the partial derivatives. So my capital Fx is going to be 2 minus lambda times 2x. My capital Fy is going to be -1 minus lambda times 4y. And my capital Fz is going to be -3 minus lambda times 6z. And we set each of these equal to 0. And there's so many different ways to do this. I feel like in class, she's been more doing what I would like to do, which is where we're kind of trying to get a relationship between x and y or between y and z. So here's one way we could do this. I like to solve each thing for lambda. So I could say, great, 2 equals lambda times 2x. And did I say solve for lambda? Yeah, I can say that's it. Yeah. Did I mean it though? I did mean it. So 1 over x is equal to lambda. Similarly here, -1 is equal to lambda times 4y. So lambda is equal to -1 over 4y. Similarly here, -3 is equal to lambda times 6z. So -3 divided by 6z, or -1 over 2z is equal to lambda. And then we set them equal to each other and get relationships between x and y, or y and z, or x and z. Okay? You just pick any two pairs. So picking the first two, trying not to squeeze everything in together. Picking the first two, so let's call this 1, this 2, this 3. If we set 1 equal to 2, we're going to get 1 over x equal to -1 over 4y. And then basically cross multiply, get 4y equal to -x, and we'll say x equal to -4y. And then you pick any other two, so either 1 and 3 or 2 and 3, and it doesn't really matter what you pick. Let's pick 2 and 3. So let's see, that's -1 over 4y equal to -1 over 2z. Cross multiply, get rid of the negatives. We have 2z equal to 4y, or z equal to 2y. And depending on which ones you picked, basically whichever variable shows up in both of them, solve for things in terms of that variable. So since y is showing up in both of these, I want x equal to something in terms of y, and z equal to something in terms of y. So I'm going to use these two things, and I'm going to plug back into my constraint. So my constraint, which was that x squared plus 2y squared plus 3z squared was equal to 30, or -30 equal to 0, however you like it. We're just going to plug in what z and x are equal to now. So I'm going to rewrite this as x, which is -4y squared, plus 2y squared, plus 3 times z, which is 2y squared, equal to 30. And then we're going to simplify and try to solve for y. So this is going to be a 16y squared plus 2y squared, and 4 times 3 is 12. Oh, good. The numbers work out nicely. Usually they'll try to make the numbers not too heinous on a problem like this. But adding up the coefficients here, 16 plus 2 plus 12 is exactly 30. So we get 30y squared equal to 30, which means y squared equals 1. So y is equal to plus or minus 1. And then we can find the other thing. So y is equal to plus or minus 1. X is equal to -4 times y is going to be minus plus 4. And z is equal to 2 times y, so plus or minus 2. So we actually have two critical points here. We have the critical point, x is -4, y is +1, z is +2. And the opposite, +4, -1, -2. Because we had that z is equal to 2y, but x is equal to -4y. So x should be the opposite sign from the whatever the y and the z coordinate is. So that's why we're getting x is -4 while the other two are positive, and vice versa. Question? So is what I did up to here okay? So right here, what I did was I solved for y, and then I said, I know that x equals -4 times y. So if y is plus or minus 1, well, if y is +1, then x is going to be -4. And if y is -1, then x is going to be +4. Similarly, if z is equal to 2y, well, if y is 1, z is going to be +2, and if y is -1, z is going to be -2. So that's how I'm getting these two different coordinates here. When y is 1, x is -4, and y is +2. When y is -1, x is +4, and z is -2. And then to finally answer the question, we go back and look at the function that we're trying to maximize or minimize, which was the temperature at x, y, z equal to 2x minus y minus 3z. So which of these 2 points is going to make this function the biggest? Is it going to be the one where x is negative or the one where x is positive? It looks like it's gonna be one more x is positive, because if you plug in a positive x and a negative value for y and a negative value for z, all those things will be positive. So it looks like the temperature at 4, comma, -1, comma, -2, which is 8 plus 1 plus 6, which is 15 degrees, whatever we're using, is the maximum temperature. And similarly, if you plug in -4, +1, +2, you're going to get -8, -1, -6, which will be -15 degrees is the minimum. So again, with Lagrange, it can be a little weird sometimes. An alternative way that probably also would have worked just fine is if we had taken each of these equations and instead solved each of them in terms of lambda. So I had written x equals 1 over lambda, y equals -1 over 4 lambda, z equals -1 over 2 lambda, plugged all those back into the constraint, solved for lambda, and then found x, y, and z by plugging the lambda value back. That would also have worked out just fine. But the problem with Lagrange is it's really kind of like, it's like a choose your own adventure. Lots of different paths will get you to the end. They might be a little bit different along the way. You're all getting, if you do this, if you do the right work, you will get to the right answer. Just your pathways might be a bit different. Excuse me. Sure.
I was doing some of the book problems and like it'll, on the Lagrange ones, it'll say like, we'll maximize this one, minimize that one. And it just kind of works, but.
Right. And yeah, and no, it's one of the challenging parts of Lagrange is that you get this critical point and then you just have to kind of justify to yourself that it is actually a maximum or minimum. So in the problem we just did here, we got 2 critical points. We plugged one of them in and got a value, and got plugged in the other one and got a different value. So we just were able to say, well, the bigger value should be the maximum and the smaller value should be the minimum. But yeah, it's a frustrating aspect of those problems. Typically, when we do these problems, we are often asked, like, right, like you're saying, like, find the maximum, and you get one critical point. We're like, well, I guess that's the maximum. But I'm sad to say there really isn't a better way to kind of talk about that. Okay, you sure? I'm happy to say things. Okay. Feel like you would all like to do another one. Yeah, whatever. That's not too bad.
But so you can. On ones like this, you can plug it in the original equation and you get. Bigger one is the maximum, the small one is the minimum.
Right, exactly. So I'm just taking my 2 critical points and exactly plugging them back into the function that we were trying to maximize or minimize to see which one gave me a larger value, which one gave me a smaller value.
What about saddle points? Is that a thing here?
That could be a thing, yes. But so I would say it is possible that when you're trying to maximize or minimize something with Lagrange multipliers, you could end up finding a critical point that actually is a saddle point. But that typically doesn't happen if the problem has been written well. So someone has thought ahead, that's usually not going to be an issue. But you're not wrong to want to consider it. Thought I had one. Where'd you go? 1 second. I had one that likes to look good. There we go. Sure. Sorry. All the problems I have, I'm like, I don't, as I look at them closer. Sure, I guess we can do that. This one says to use a Lagrange multiplier to find the minimum distance between the line x minus y equal to 4 and the point 0, 2. And to me, this seems like a problem where I would not typically use Lagrange multiplier for it to be. But that's fine. So we're trying to minimize the distance. And the distance between the point on this line, which I'm going to call x comma y, right? Here's my line, x minus y equal to 4, which is just this line here. Y equals -4. So some point on this line and the point 0, comma 2. So I'm trying to minimize that distance there. So by the way, when we find this point that minimizes the distance, the way we're going to justify that it's in fact the minimum is, well, it couldn't be a maximum because you could always find a point on the line further and further away from any other point. So you can keep finding further points. So it's definitely not a max, so it's got to be a min. And that's the kind of weak justification that we often offer for problems like this. We're like, well, it couldn't be a maximum, it's got to be a minimum. So here's our distance formula. The distance between the point 0, 2 and any old point x comma y on my line is going to be square root of x minus 2 squared plus y minus 0 squared. Then, no, sorry. Then I was going to try and see, this one's hard for me not to want to just do. To me, I made a mistake though. I definitely made a mistake in my distance formula here. It should be x minus the x coordinate, and the x coordinate of the point is 0, not 2. So I made an error there. I apologize. I'm trying to minimize the distance equal to the square root of x minus 0 squared plus y minus 2 squared. And to me, if I were doing this problem, I would do it not with Lagrange multipliers. The way I think you should do this problem, in fact, we'll do it both ways here, is you should plug in what y is equal to. Plug in the constraint to y right here, and then you have a function of one variable that's very easy to, right? We wouldn't even need to use the second derivatives thing. We just would do it the normalish way. But let's use Lagrange because. So we're going to minimize this, and our constraint is that the point has to be on the line. So our constraint is that x minus y has to equal. Yeah. And here's what you should always do if you have to minimize the distance or maximize the distance. Maximize or minimize the square of the distance. So instead of this, we're going to say that d squared is equal to just x squared plus y minus 2 squared. It's always the better choice. I don't usually say always, like I often hedge, but I've never found a time where it's not better to do the square of the distance. So if you're minimizing a distance, I would say always minimize the square of the distance. So here's our thing we want to minimize. We're minimizing, and I just wrote, I'm writing again, I'm aware of that. Minimizing x squared plus y minus 2 squared. Our constraint is x minus y minus 4 equal to 0. So our f of x comma y comma lambda is x squared plus y minus 2 squared plus lambda times x minus y minus 4. Taking our partials, capital Fx is 2x plus lambda times 1. Our capital Fy is 2 times y minus 2 plus lambda times negative 1. Yeah, it's just the way I like to do it. I would solve for lambda here. It just feels like the way it's meant to be done. So solving for lambda, I get 2x equal to lambda. Great. Here, oh, sorry, equal to negative lambda. Be careful, James. So negative 2x equals lambda. And here, adding lambda over there, I have 2 times y minus 2 equal to lambda. And then I would set those equal to each other to get a relationship between x and y. So I'm going to have that negative 2x equals 2 times y minus 2. And I guess since x is pretty much already isolated, I might as well just solve for x here and say that x equals 2 divided by -2 is -1 times y minus 2. Or multiplying it out, x equals 2 minus y. So that's what I'm going to plug back into my constraint. So my constraint was x minus y equal to 4. I'm going to plug that in for x and get 2 minus y equal to 4. So it looks like 2 minus 2y equals 4. So y is going to have to be -1. Which means then x is going to be 2 minus -1, which is +3. We found the point that's closest, but the question was very specific. The question said, find the minimum distance. So this point's the closest. 3, -1 is the closest point on the line x minus y equals 4 to the point 0, 2. But if we're answering the question completely, we have to actually find what the distance is, because the problem said find the minimum distance. So the minimum distance is the distance between these 2 points. So it's the square root of 3 minus 0 squared plus -1 minus 2 squared. And then whatever that ends up being, it's the square root of 9 plus 9, which is the square root of 18. So just be careful when you're reading the question. Make sure you're actually, especially with these optimization ones, make sure you're answering the actual questions being asked. I could have just as easily said, find the point that minimizes the distance, and then the correct answer would have been the point 3, -1. All right, let's do a double integral. Yeah, we got time. Let's look at this double integral. Yeah, I got one. So I'm going to evaluate the interval from 0 to 8, the interval from y to the 1/3, 2 of 6y over square root of 1 plus x to the 7th, dx dy. And I have to imagine that you're going to get asked a double integral, and it's going to be written in the wrong order of integration. And you're going to see this, and maybe they're going to tell you have to switch them. Maybe they're not going to tell you. But you're going to see that and be like, well, I don't know how to integrate 1 over the square root of 1 plus x. So I'm ignoring the 6y. I'm thinking of that really as 6y times 1 over the square root of 1 plus x to the 7th. And if I was integrating with respect to y first, that'd be great. The antiderivative of 6y is just 6y squared over 2.
That I will write question the way they write it on the homework problems, where it's like, it's not, you have to put in the numbers for the double, which I usually I can do.
When you say put it, like, you mean like have?
Yeah, I won't write it like that. It'll be like, you know, a sentence
I'm not sure, like in the textbook.
For the homework problems.
Oh, like
It's not that.
right now I'm thinking of like the web work problems, and like
Yeah.
it's like, and they're kind of asking you to like find limits of integration.
Yeah, and it'll give you x, maybe one of the x's, and you assume you have like zeros.
Okay. I don't know. I mean, so if I were giving a double integral question like this on the exam, I would typically give you the entire double integral. And I might give you the instruction that you need to change the order of integration, or the hint. But definitely, so if we're going to change the order of integration, what we need to do is draw the region of integration. So drawing the inner limits of integration, I know that my lower bound is, or sorry, I should say my left bound really is x equal to y to the 1/3. I am not great at graphing that. I'm not great about thinking about what that graph looks like. So before I even try to graph that, I'm going to rewrite it as x to the 3rd equal to y, just because I'm better at knowing what that looks like. Oh, I know what that looks like. It looks kind of like this. There's my y equals x cubed, or my x equals y to the 1/3. And then drawing x equals 2 is not terrible. It's a vertical line. Something like that. So my strip, when I wrote it like this, my horizontal strip looked like that. It was going from as far left as x equal to y to the 1/3 to as far right as x equal to 2. And then that strip went as low as y equals 0 to as high as, I bet that point is y equals 8. Because if x is 2, oh yeah, if x is 2, 2 to the 3rd is equal to 8. So here's my region. Now we're going to redo it using a vertical strip. Now, for our inner limits of integration, which we're going to be at dy now, we're going to go from a low of y equals 0 to a high of the function, which is y equals x to the 3rd, right? Because we're switching from a function of x to a function, sorry, from a function of y to a function of x. And our outer limits of integration are going to be as far left as x equals 0 to as far right as x equals 2. And we still have scrunched in here the 6y over the square root of 1 plus x to the 7th. So now we can do the integral. And if it's something like this where it seems like it's easy to like write the x parts multiplied by the y parts separately, it's perfectly fine to do that. I think it's worthwhile to rewrite this integral as the integral from 0 to 2, the integral from y equals 0 to y equals x cubed of 1 over the square root of x, sorry, 1 plus x to the 7th times 6y dy dx. So then the part that's acting like the constant, you can kind of just think of as the constant in front. So when we do this first integration, and I do really like parentheses around what I'm doing first. So there's what's happening first. The integral from 0 to 2 and the dx are just kind of taking up space for the moment. So when we integrate this, the antiderivative of 6y is going to be 6y squared over 2, 3y squared. So we're going to get still the integral from 0 to 2, still the dx on the outside, but on the inside now, we're going to have the antiderivative of this, which is going to be the 1 over the square root of x of 1 plus x to the 7th just hanging out. And then you're going to have your 3y squared. Evaluated from y equals 0 to y equals x cubed. And we plug in. And we get integral from 0 to 2. We get 1 over the square root of 1 plus x to the 7th times 3 times x cubed squared minus 3 times 0 squared. Which I normally probably wouldn't. We can see that this is going to be kind of nice. It's going to be the integral from 0 to 2. X cubed squared is x to the 6th. It was 3x to the 6th over 1 plus x to the 7th squared. And most of the time, these ones go where you have to switch is you do the switch, something nice kind of happens, and then the integral you're left with has like kind of a perfect u substitution. That really happens a lot of the time if you're having this thing where you have to switch it to make it even more. So then we're going to do a u sub. We're going to let u equal 1 plus x to the 7th, where du is going to be 7x to the 6th dx. I'm going to have a 1/7 du equal to x to the 6th dx. So when we rewrite this, we're going to get the integral of 3 times x to the 6th dx. That x to the 6th dx is going to be my du over 7. So it's going to be 3 times du over 7 over the square root of u. Should we change the limits of integration? Yeah, I feel like we should. They're not too terrible. If x is 0, which it was, then u is going to be 1 plus 0. And if x is 2, u is going to be 1 plus 2 to the 7th, which is, okay, it's not lovely. 2 to the 7th is 128, so 129. right? 2 to the 5th is 32, 2 to the 6th is 64, 2 to the 7th is 128. Yeah, we're good. Okay. So then a little rewriting. Let's bring the 3/7 out in front. Integral from 1 to 129 of, let's say this is u to the -1/2. And then we have to differentiate. We get 3/7 times 2u to the 1/2. It's a 7, not a 2, James. And then we end up with 6/7 times 100. Oh, don't forget the 1 to 129. 6/7 times the square root of 129 minus the square root of 1. And that's the area, no, sorry, the volume of the thing that we just found. Okay. 5 minutes left. With a brief, oh, and just so I won't do one. I'll just remind you that if someone had to find the average value of that, you would just take the thing we just found and divide that by the area of the region. So just as a reminder, the average value would be that thing we just found divided by the area of the region, which you would just find by doing the same double integral without any limits of integration. Sorry. Same double integral without any integrand, opposite kind. So that'd be like the 6/7 times whatever on top. And then on the bottom, you'd be doing the double integral from 0 to 2 and from 0 to x cubed. But now you're just doing the double integral of 1, which is not quite so bad. And so again, average value is just your double integral of your function divided by the double integral of 1, or in other words, divided by the area of the region. And if the area is like a triangle or a circle, you can just use your known areas to do that. You don't have to like do a double integral. Here, you would have to do a double integral to find the area of that. Right, this the only way to find the area of that is by. I think the last thing I'll say is that for sequences in series, to show a series diverges, you can use the nth term test. So I just want to remind you, if the limit as n goes to infinity of your sequence is not 0, then this series diverges. The series from n equals whatever to infinity. On the other hand, I want to make this really, really clear. If the limit as n goes to infinity of the sequence is 0, then we don't know anything. Then do something else. So I just want to stress that if you're using the test for divergence, aka the nth term test, you can only use that test to show something diverges. If you take the limit of the sequence and you just get 0, the series could converge or the series could diverge. There's other work we have to do to figure out if it is. And the only other thing we really have available to us at this juncture is geometric series stuff. So for example, if I said, does this series converge or diverge? Well, it's geometric. It's the sum from n equals 1 to infinity of 2 times 1/5 to the n. The ratio is 1/5. If we start writing out terms, our terms are 2 times 1/5 plus 2 times 1/5 squared plus 2 times 1/5 cubed, et cetera, et cetera, et cetera. And the ratio, the thing that you multiply each term by to get to the next term, is 1/5. And that's the hallmark of a geometric series, that each subsequent term is the previous term multiplied by the same ratio. And if that ratio is between -1 and 1, which 1/5 certainly is, then the geometric series converges. So this series converges, and it converges to the first term of the series divided by 1 minus the ratio, which in this case would be 2 times 1/5, that's my first term, over 1 minus 1/5. which would be 2/5 over 4/5, which reduces just to 1/2. So, yeah. Yeah, those are really the only series convergence tools we have at this point on the test, is geometric or being divergent by the nth term test.
By the way, showing the multiplier.
Exactly, the multiplier, yes. And so typically when you see something like this, it's going to be the thing that's raised to the end. So if that had been like a 2 times 5 to the end, it'd still be geometric, but then the ratio would be larger than 1, which means the series would diverge. You'd be adding up a bunch of terms that got larger and larger.
Start at n equals 0.
Good question. What if I did start at n equals 0? Then the sum from n equals 0 to infinity of 2 times 1/5 to the n still converges because it still meets the criteria having the ratio between -1 and 1. But now it's going to converge to its first term divided by 1 minus the ratio. And the first term here, if I plug in 0, is 2 times 1/5 to the 0, which is just 2 times 1. So this converges to 2 over 4/5, which is going to be 10/4, which is 5/2. Not surprising if you think about the previous one. The previous one converged to 1/2, and all I'm doing here is I'm adding on the first and one more term. So really, this is equal to, if I plug in 0, 2 times 1/5 to the 0th, plus 2 times 1/5 to the 1, plus 2 times 1/5 squared, plus 2 times 1/5 cubed, et cetera, et cetera, et cetera. But we just figured out before that these parts add up to 1/2. So clearly, if I add on a 2 in front, it's got to add up to 2.5, which is 5/2. But this general version of this idea for a geometric series, that it's always going to, if it converges, converge to the first term of the series divided by 1 minus the ratio, is always correct. It's not always taught that way. I will finish writing the practice exam, post it, and post solutions tomorrow, which still should be enough time to like take a look at it and get some practice out of it. All right. I will see you all on Wednesday after your exam. You're welcome.